standing waves. This. Okay. So with a standing wave, we're taking those principles of superposition of constructive and destructive interference. Right? Constructive is when the amplitudes add. Destructive is when they subtract. Right? Again, destructive, I like to say, is you're taking like a hole and you're filling it with dirt. Right? And constructive, you're either taking two piles of dirt and making a bigger one, or you're digging deeper holes. Right? So what happens with a standing wave is, imagine we have a string and it's connected between two stops, two walls or whatever, right? If we send a wave down, right, it's going to come down, it's going to hit here, and then it reverses, right? It's reflected, but it's now on the bottom. You saw that, right? If it's a fixed end, it comes this way, but then when it hits here, it's reflected underneath, right? Does that make sense? Okay. So with a standing wave, you've got a wave coming this way, but then you have a wave bouncing off and coming this way, and it's going to interact with the waves that are still coming back, right, or that are still being created. So what happens is eventually they start to go through constructive and destructive interference as they go through. Does that make sense? You follow me? All right. So you'll see a wave then that eventually is going to form that looks like this. Right? And the wave is going to go up and down, up and down. It's going to look like it's just going up and down, hanging out in space. Right? Like it's not moving, it's just doing this. Okay? So this would be on the top, and I put the bottom on to look dash, but it travels through that whole amplitude range. Okay? The reason why it's traveling up and down like that is because you have the waves coming this way interacting with the waves coming this way, so that sometimes they're adding and you're getting the really tall peaks, and sometimes they're subtracting, right, and you're getting the zeros, and you're getting those spots in between. Does that make sense? Okay? So that's how superposition relates to creating a standing wave. The wave isn't actually standing. It's not hanging out just to be like, right, hello? It's not doing that, right? It's just all the waves that are being created superimposing on each other, going through superposition, going through constructive and destructive interference. Does that make sense? Bob, you look like you're deep in thought. Okay.
So you say that like all the waves that are creating cancel each other out?
No, they're adding and subtracting depending on their position. It's really hard for me to draw. One, because I'm a very poor artist, and two, because it's hard to draw. But there's a good diagram in the book, in the green book, that shows, all right, if the wave is this wave is right here, and this wave is right here, we don't see anything. But then if this wave is here and this wave is there, it kind of fills in a little bit, right? But there's still two separate things. And then if this wave is here and this wave is here, we get zero, right? Because they're subtracting, right? So that's what they're doing, is they are showing like little bits and pieces of the wavelength, and as they interact. And it just so happens that, again, when these go through, right, you get the little pieces here adding, and then subtracting as they go through that. And it looks like it just creates this. Okay? But there are waves traveling through here the whole time. Okay? So there's a couple things that we need to look at if we're going to talk about standing waves. The first thing is called a boundary condition. Okay, and this boundary condition is very, very simple. Okay? The waves need to end at a node. And we'll talk about nodes in a second. Okay? And it is set by the length of the string.
Is this only in string? We talk about guitar strings a lot.
Guitar strings, same exact way.
But is it only in strings or is it all?
No, because when we talk about sound on Friday,
They have standing waves too.
yes, but they act differently. Okay. Right. So they create standing waves, but differently because they're not transverse waves. Okay. So again, our boundary conditions are that waves need to end on nodes, okay? And it's set by the length of the string, or essentially the boundaries, right? Where these, if these are our walls, right? These are our boundaries, okay? The waves have to be fixed right here. I mean, physically, think about it. It's obvious, right? Okay? So if this is L, what would the wavelength be for this wave? 2L, right? Because this is one piece of the wave, but a full wave is this, right? So the wavelength for this wave would be 2L? Right? Okay? All right, but we'll get there. So this and that have the same amplitude? Say that again?
Like the beginning node and the end node are the same amplitude.
Well, the amplitude is 0, right?
Wait, you said it's 2L, right?
The wavelength is 2L. Oh, so yeah, if we constructed it back out, this would also be L, right? Okay. All right, so what is a node?
A node, it's a place where a wave stops.
It's where it doesn't move, right? So this would be a node, right? Doesn't move, it's a place where the amplitude is 0, right? It looks like that piece of the wave, a piece of the string is just hanging out in space, it's not moving, okay? What is this spot right here? Right, it's an antinode. And that's the spot where it's at its maximum amplitude, okay? At its maximum amplitude at an antinode, the amplitude at a node is 0,
Who came up with this book?
okay?
Doesn't matter if it's a max positive and negative.
No, because they're the same. Because you think about it, this wave, it's one string doing this.
So like if it was on the bottom, that would be
Yeah, yeah. Because it can't have one amplitude here and then a different amplitude on the bottom. Okay?
So antinode down and
No, an antinode could be right here as well. Because it's just the piece of the string, it's a location on the string, it's not a location in space. Okay? All right, so here would be one node. One, we'll call it frequency, right? If we got it going, again, we changed the frequency, but we kept the boundary conditions the same, we may get one that looks like this now. That's not good. Right? We'd get something that looked like this. Same L, but if we increase the frequency, we now have something that looks like that, right? What's wrong? Okay? If we do it again, that's not good. Let's try that again. Yeah. All right, we'd get something like that. Does that make sense? So what is the wavelength here? This wavelength here is equal to 2L. What is the wavelength here?
4L.
L, right? The wavelength here is equal to L, correct? What about the wavelength here? What is this equal to? 2/3 L, right? Okay? Awesome. So all I did with these three different pieces is all I did was I just drew the next section that I could get in where I'd have another node. Okay? So all I did when I was drawing these is I just drew them so that I would get another node in there. All right? Because remember, the boundary conditions say that I need to start and end at a node. Okay? So what kind of relationship do you see we've got here? We've got 2L, and then we've got L, then we've got 2/3 L, right? What do you think the next one would be if we went to 4? 1/2 L, right? So can we come up with some sort of relationship that works with all, that can describe every single, essentially different frequencies, or we call them harmonics? So what can we say? What can we say about the wavelength?
2L over the number of amplitudes.
All right, so it's 2L over right? Good. So the wavelength for a standing wave is going to be equal to 2L over m, where m is equal to, they call them the modes. Okay? Sometimes you see it as like n because they're talking number, but our book uses m. Okay? So if you look at this, right, when m is 1, which would be the fundamental, the first one, we get a wavelength of 2L, right? When we made it a full wavelength, right, m would be 2, we got a wavelength of L. Right?
That M is the number of nodes.
Okay? So all we're just calling, they call it the mode for now, and really what we're talking about are harmonics. Okay? So when we had the third one, right, m would be 3, we got 2/3 L, correct? And that wavelength fit in there perfectly. Okay? Awesome. So what we can say is that this mode, m is the mode, it's equal to the number of antinodes. Right? It's equal to the number of antinodes. So that's one way you can think about it. If you're going to draw it and you got a mode of 4, make sure you draw a wave that has 4 antinodes. Good? Okay? Something to look out for. So let's put this together, and I want to be able to now use this information to predict the frequencies where these are going to happen. Follow me? So I want to be able to now take this information and predict the frequencies where these different waves are going to occur. All right? So we know speed of a wave, bingo, bango. All right? So what I can do then is I know that lambda, right, is equal to 2L over the number of the mode. Okay? I should get some space. Okay? So then the frequency is going to be equal to the number of the mode, V over 2L. Okay. Now, if you think about this, if you look at this information, the speed of the wave is not going to change. If you keep the tension the same on the string, you keep the mass of the string the same, the speed is the same, right? If we go back to what you learned in that last activity, what we started the class talking about, right? We found that V, to jog your memory, is equal to T over mu, right? And if we keep these two things the same, so we just don't change the string, right? This V stays the same, okay? So the L isn't going to change at all either, right? Unless we're changing the moving walls in this instance, or over there we're sliding it over. So the frequency then is just the function of the mode that we want, or the harmonic that we want. Does that make sense? Because this whole thing isn't going to change. So if I know one of the frequencies, I can pretty much get all of them. I can predict every single one down the line because I'll know this stuff. Does that make sense?
So once you know the speed, and once you know the length, then you can just predict.
Yeah, and you can know that. You got your string, you can measure how long it is, you can measure the density, and you can figure out exactly what V is going to be, right? And again, you know the length, so that's good to go, right? And then you just put it together, you cause us to create a standing wave, and you just count the number of antinodes, and then you know what mode you have. And then from there, you can predict any frequency you want. Right? So what we can say, yep. Remember that V for a wave on a string is the tension divided by the mass density. So as long as you pull on the string with the same tension, right? And as long as your string doesn't change its mass density. Right. So I mean, unless and you're not gonna change the string halfway through a cycle, right? So it's always going to be the same. All right. So this number then just becomes a constant, right? And then it's just whatever mode, whatever frequency you want, okay? So if we take this and we apply it to the first harmonic, right? So instead of calling them modes, we can also call them harmonics. The first harmonic, we would have a frequency of V over 2L. Correct? All right. And then just to make it a little nicer, a little more simple, that then means that the frequency of any harmonic that we'd want is equal to M times the first one. Does that make sense? Right? So now, any frequency that we want is just an integer multiple of the first one. Okay? Think about in music. If a note, I don't know what's 220 hertz. What note is that? You don't know. Okay. 220 hertz. You want to play, all right. You want the next octave? It's going to be 440. You want the next octave after that? It's going to be 660.
Why do you add 220?
I'm sorry, 220 is the first one.
Oh, okay. You said 200.
440 should be the next one. 660 should be the next octave after that. Okay?
Adam thought he knew music.
Okay.
And now he's lost.
Well, no, because no, it's three. It's whatever this is times the fundamental. But either way, I don't know frequencies and notes, but all right.